Hello everyone. We have two expressions given here and we'll have to prove that one is equal to another. So on the left hand side, we've been given that tan theta plus secant theta minus 1, the whole thing divided by tan theta minus secant theta plus 1 is equal to 1 plus sine theta by cos theta. This is our right hand side. We'll have to prove that this is equal to the other one. Now at one look at it, we have tangent and secant on one side and we have the sine and cosine on the other. So let's explore further in another page what the right hand side actually indicates. So it was 1 plus sine theta by cos theta. The denominator can be written common to both 1 by cos theta plus sine theta by cos theta, because this is a single denominator here. We can split it and write it this way. So what is 1 by cos theta? Always secant is the cosine is the reciprocal of secant theta, or in short we write it as sec theta. So let me write it as sec theta as it is written always. It's secant theta plus, and sine theta by cos theta is nothing but tan theta. So we'll have to prove that the whole of this, the left hand side, is equal to what? Just secant theta plus tan theta. Now at least the expressions are almost like we'll be able to do something about it, because both have secant and tan. So let's further see how to go about it. Now what is the only relationship which we know between tan and secant? Now we'll have to recall the Pythagorean identity for this. We have the trigonometric identity, the trigonometric Pythagorean identity, which we have proved in one of our math decoded videos. Sine squared theta plus cos squared theta is equal to 1. If you divide this throughout both sides by cos squared theta, what is that which we get? We have done this also before, but just for recollecting, sine squared theta by cos squared theta is nothing but tan squared theta plus 1 is equal to secant squared theta. Now we have arrived at a relationship between the tan squared theta and secant squared theta, and we can manipulate this relationship as we want, meaning we can in fact subtract 1 to both sides and write that 1 secant squared theta minus 1 is equal to tan squared theta, or we can also subtract tan squared theta to both sides and write it as secant squared theta minus tan squared theta is equal to 1. I hope I am right. Yeah, tan squared theta is equal to 1. So let's try to use maybe one of these or more than one of these in proving this expression, that this left hand side is equal to the right hand side. Now in order to make use of it, we need tan squared theta and secant squared theta. We don't have tan squared, so how do we get it? We just have tan theta and secant theta. So let us try multiplying the expression which is given here by, for that purpose we'll have to recall this algebraic identity which we have learnt in our earlier classes. A plus b into a minus b. This is equal to a squared minus b squared. So what if you consider a part of it as a and another part of it as b, and multiply by a minus b so as to get squares on the tan squared and secant squared. So let us try and do it. Now for that purpose, let me rearrange both the numerator and the denominator. Tan theta minus 1 plus secant theta. You would have guessed now why I am writing it as tan theta minus 1, because of this identity which we have here, right? We can make use of these things. That is why we are rewriting tan theta minus 1 plus secant theta, the whole thing divided by the denominator also can be rearranged, tan theta plus 1 minus secant theta, and let us multiply this by if you consider tan theta plus 1 as A and secant theta as B, this is A minus B. So let's multiply by A plus B. This is a popular method of multiplication. This is called as the conjugate of the other. You will use it as and when you solve for the sums. So tan theta plus 1 plus secant theta, right? And whatever is multiplied in the denominator, the same expression has to be multiplied in the numerator also, so as the value of the fraction is unaltered. So we have multiplied both the denominator and numerator by this. Now we are considering this as A and secant theta as B, right? So here also tan theta plus 1 is A and secant theta is B. So what happens to the denominator? It becomes tan theta plus 1 the whole squared minus secant theta the whole squared, or I can write it as secant squared theta. Fine. And now look at the numerator. Do we have any A plus B into A minus B here? No, I don't think so. But if you can once again rearrange this, in the sense, if I shift the minus 1 here and this plus 1 is written here, if the addition is commutative, we can always rearrange things. So now if you rewrite it in that way, we will have tan theta plus secant theta as A and 1 as B, right? So let me rewrite it. You have tan theta plus secant theta as A, right? So when I multiply, it becomes square, and your B is, here it is minus 1 and here it is plus 1. So 1 squared, which I can write as 1. So this is what our numerator now indicates. And let me simplify this further. So now this is in the form A plus B the whole squared, right? So expanding it, I have tan squared theta plus secant squared theta plus 2 tan theta secant theta minus 1, and the whole thing divided by, what about the denominator? It's tan theta plus 1 the whole squared. So tan squared theta plus 1 squared, or I just write it as 1 plus 2 tan theta minus secant squared theta. Now let us look at what we can do, how we can simplify this. Let me look at the next page for it. We have a secant squared theta minus 1, and here also we have a 1 minus secant squared theta, or we have a tan squared theta plus 1. Let's see what we can do about it. Yeah. Yes, secant squared theta minus 1 can be written as tan squared theta, right? So let's do that first. So here in the numerator we have 2 times tan squared theta, because we have written secant squared theta minus 1 as tan squared theta again. So this becomes 2 tan squared theta plus 2 tan theta secant theta. This is our numerator. And what about the denominator? Let us write tan squared theta plus 1 as secant squared theta, isn't it? Here, tan squared theta plus 1 is equal to secant squared, or am I, yeah, tan squared theta plus 1 is equal to secant squared theta. So what do we benefit by writing like that? We have the secant squared theta cancelled. So this is secant squared theta plus 2 tan theta minus secant squared theta. So secant squared theta minus secant squared theta becomes 0. So the denominator is left just with 2 tan theta. And the numerator also, 2 tan theta can be factorized as it is common to both the terms here. So 2 tan theta into tan theta plus secant theta, and the denominator has 2 tan theta, which can be cancelled because they are common in both numerator and denominator. So finally we are left with tan theta plus secant theta. See, and that is what we actually wanted, right? 1 plus, which is equal to 1 plus sine theta by cos theta. Of course we can come to that in the previous sum itself, we can say that this LHS is equal to RHS by rearranging this. Tan theta plus secant theta can be written as, let me change the color, sin theta by cos theta plus 1 by cos theta, or this is equal to 1 plus sin theta by cos theta. So this is your RHS. Now look at your problem. 1 plus sin theta by cos theta. We started off with this bigger expression, and we have proved that this is equal to 1 plus sin theta by cos theta. See, in the process we haven't memorized anything. We have just rearranged terms, and we have used these algebraic identities, and we also use the trigonometric Pythagorean identity, sin squared theta plus cos squared theta is equal to 1. Thank you. I hope you followed this problem.